In this video, we cover ideal transformers. An ideal transformer is a device that does its job without any loss in the process. So that would mean that the ratio of the primary voltage over the secondary voltage must exactly be equal to the ratio of the primary turns over the secondary turns. We call this ratio the turns ratio A. Likewise, the ratio of the primary current over the secondary current is exactly equals to the ratio of the secondary turns over the primary turns. And that should give us the reciprocal of the turns ratio. In phasor form, the ratio of the primary over the secondary voltages must also be equals to the turns ratio, and the ratio of the primary current over the secondary current in phasor is also equal to the reciprocal of the turns ratio. Uh, Take note that A here is a constant, so that means that in an ideal transformer, the primary voltage and the secondary voltage are in phase, and the primary current and the secondary current are also in phase. That would also mean that the phase angles of the primary and the secondary must be the same, and the phase angles of the currents in the primary and secondary are also the same. In an ideal transformer, whatever power that comes in the transformer must come out of the transformer. So that means if the power going into the transformer expressed in that manner must also be equal to the power at the secondary side. Similarly, for reactive power, whatever reactive power that goes in the transformer must come out of the transformer. And the same goes to the apparent power. Whatever comes in must come out. Take note that with these relationships, that means that the power factor at the secondary, the power factor angle must be equal to the power factor at the primary. Now, one interesting characteristic of transformers is how it changes the value of the impedance that is connected on one side of the transformer as seen from the other side. Let's say we have an impedance E sub L connected at the secondary side. It is interesting to know how it would measure if we look at it at the primary side. So let's say that this impedance looks like a Z sub P on the primary side. So that means I can replace this whole thing by this and still get the same primary current. Okay, and the relationship between Z sub L and Z sub P is actually given by this. Okay, so how did that uh, relationship, uh, how did we derive that relationship? Take note that in the primary, we have this relationship in the apparent power relationship or the Ohm's law relationship that the voltage uh, on the primary must equal the current that goes to the primary times Z sub P. Okay, so this is a simple Ohm's law. On the secondary, using Ohm's law as well, the secondary voltage as equals the secondary current times Z sub L. Okay. Let's say I divide this equation with this equation. That means I will get there V sub P over V sub S as equals I sub P Z sub P divided by Z sub L. So this one is the turns ratio, P, while this one, um, so we have here I sub S, and this one is the reciprocal of the turns ratio, C sub L. Okay, so solving for Z sub P, that will give us A squared C sub L. Okay, so which is this relationship here. So that means, let's say our A is 10, which is a step down transformer, and we have Z sub L equals to 1 ohm. So that means if I look at the primary, Z sub L would look like 10 squared times 1, and that is equals to 100 ohms. Okay, so that is the effect of transformer on the um, impedance. Let's take this example. Let's say I have a load 4 plus J3 ohms, and that load is connected to a 480 volt generator via a transmission line that has a small impedance. So first, we need to find the voltage at the load. Okay, so this one, this voltage, and the losses in the uh, process. That is, in the process of transmitting power to the load from the source using this transmission line, what is the losses, the transmission losses. And B, okay, so we do the transmission without any uh, transformer. In B, we use a transformer. So first, we put here a step-up transformer before transmission, and then after transmission, we put another transformer. So it's called a transmission or transformer 1. We call this transformer 2. And we repeat the process. Um, we compute for the voltage at the load and also the transmission losses. Okay, so without the transformer, we can compute the voltage at the load simply using a voltage divider. So 480 times the dividing factor, and that should give us this one. So notice that we get a voltage that is lower than the source voltage, uh, and almost a 30 volt penalty with respect to the source voltage of 480 volts. We can compute for the uh, current through the circuit. So we get this current and this phase angle. Computing for the transmission losses, we simply multiply the square of the current that passes through the transmission line with the resistance of the transmission line, and that should give us this much transmission loss. So it's approximately 1.5 kilowatts. Now let's say we do the same transmission, but this time uh, we first step up the voltage of the source using a step-up transformer with a turns ratio equals to 1 over 10. So this is 0.1. And then transmit the power, and at the other end, we step it down using a step-down transformer with a ratio equals to 10. Okay, and then we connect the load at the secondary side of that transformer. Now to solve this voltage and the transmission loss, we need to reflect the impedance on the other side of the transformer. So, for example, this impedance would look different in the primary. Let's call that impedance this one. Okay, so based on our discussion a while ago, this impedance would look like 10 squared times the impedance, and that should give us this value. So this impedance here looks like 400 plus J300 on the primary side of transformer 2. Um, so that means that this now can be replaced. This whole thing can now be replaced by this one. And that would be in series with this. So therefore we can uh, add that this impedance to this, and that should give us this. And we also reflect that impedance on the other side of transformer 1, on the primary side. So therefore we uh, again use the formula for the translation, and we multiply it by the turns ratio of transformer 1. And that should give us uh, this one. Okay, so that means the generator is simply connected to an impedance. So this is 480 volts, which is 5 angle 36.88 degrees ohms. Okay, so the previous slide is shown here again with the load and the second transformer replaced by this impedance. Um, so now that we know that the generator is simply connected to a single impedance, so this is our generator here. This is connected to this impedance. We can compute the current I sub T, this current here, which is the primary current going to the first transformer, and that should give us this value. We can also compute for the current on the secondary side of the first transformer, which is this one, using this relationship. Okay, and that should give us this current. We can also determine the secondary voltage of the first transformer using this relationship, and that should give us this value. We can compute for the voltage, the primary voltage of the second transformer using the voltage divider. Okay, and that should give us this result. Now, going back to the original illustration, now that we know this, we should be able to get the secondary voltage of the second transformer. So this is the secondary voltage here, and we can use this formula to do that, and that should give us this result. Now we know that the load is directly connected to the secondary of the second transformer. That means that the secondary or the load voltage must equal to the secondary voltage of the second transformer. And that should give us this voltage, which is very much close to the voltage of the source. And likewise for the phase angle, it is almost the same as the phase angle of the source voltage. For the transmission loss, uh, we know this current. So we simply square this and multiply with the resistance of the transmission line, and that should give us this loss. So it's just 17 watts of transmission loss. Now, in summary, we can now compare the results without transformer and using a transformer. For the load voltage, the voltage using a transformer, the voltage is almost the same as the source voltage. So the voltage drop is very minimal. And for the transmission loss, there's a very big difference between the losses using without transformer and using a transformer. So this example shows how using a transformer solves the problem of voltage drop and the losses in the process of transmitting power from a source going to a load over a transmission line that has an impedance. On our next video, we'll cover the characteristics of transformers without load.